Okay, hi everyone, welcome back. We are covering DQNs and policy gradients today as part of our reinforcement learning module.
Okay, all right. So hello everyone, welcome to the third lecture on reinforcement learning. Let's see where we are right now. We have looked at MDPs and RL now. We looked at what are the assumptions we make in reinforcement learning, where we don't have access to the rewards and transition function. And we also saw the setting of deep reinforcement learning, where we need function approximation to understand large dimensional state spaces. For today, we're going to now focus on some RL algorithms. Namely, we're going to first talk about what types of RL algorithms there are. And then we're going to specifically look at one particular algorithm in the value-based side, which is deep Q learning, and one algorithm in the policy-based side, which is policy gradients. So let's start now. And before I head into that, I want to give a quick recap on something we discussed in the last lecture, which may have been hard to understand. I'm going to revisit the recursive Bellman expansion, and I'm going to now derive it in terms of the definition of the Q function. So if you recall last time, what I had done was that I had written the optimal Q function Q star in terms of itself with a reward and a next state distribution. So that may have been a bit hard to understand. So let me try to derive that again from its definition itself. So here on the right hand side, I have written the definition of Q star. And this may look different from what you saw earlier because I have explicitly written down every single term in the expectation. So the randomness is coming from my action sampled from the optimal policy pi star and my next state sampled from the transition distribution P. And what I have inside is the same thing as before. It's the sum of discounted future rewards, which I now call as the return starting from t equal to 0. And the first state and the first action are fixed because those are the inputs to my Q star. Q star of S comma A is the expected reward I get starting from state S, taking action A, and thereafter following the optimal policy pi star. This is the definition of Q star. And if you think of this as a summation starting from t equal to 0 to infinity, let's try to break this into two parts. Let's first write the first term just for t equal to 0. So it's going to be just the reward at t equal to 0. And what we're going to write on the right hand side is the return starting from the state which is reached at t equal to 1. And now, since there's an expectation of our next states here, it's going to be the expected next state at t equal to 1. And it's going to be multiplied by a factor of gamma, which you'll see now. So what I've shown you here is this basically the first term of this summation, which is gamma power 0 times the reward of taking action A at a state S. And the right is basically what is the expected state after one time step. So after taking action A at state S, what is the expected S prime that I will reach? And what I've written here is just trying to get the same expression as I had earlier, because now when I have this expression of expectation over actions AT and states ST, and I have the gamma power T and R term here, this is going to look very similar to what I had earlier. And this entire term is going to collapse into my V star. And why is that the case? If you just recall the definition of V star of S prime is asking what is the value of starting from state S prime, or in other words, what is the discounted reward I will get starting from state S prime. So this S1 equal to S prime is asking when I start from state S prime as my first state, what is the discounted reward I'm going to get? And in order to get the same gamma factor, I had to take one gamma outside over here, which you see appears here. And I'm going to now drag it outside of this expectation over here. So with this, I have now written my expected sum of discounted reward starting from t equal to 0 to two parts. One is the reward at t equal to 0. And then this is gamma times the expected value at the state at t equal to 1. And this is basically how I was able to derive the recursive Bellman optimality equation for Q star. And after this, you can just follow the same thing as I written in yesterday's slides, where you can replace V star again with the max over actions of Q star. But this is the new intuition, and this is the way of deriving the optimal Q star just from the definition of Q star itself. So are there any questions on this?
There is a question. Someone is having difficulty understanding the expectation of expectation expression, and I suspect that's happening in line number 2.
Okay. Uh, I don't understand that. Yeah. Okay. So is it, so the reason I've written two expectations here is that, so what is this expectation on the left hand side? I've done a bit of notation abuse because I've written the expectation over actions for all time steps with just one AT. So this is actually an expectation of actions AT where T is going from 1 to infinity. And same here, this expectation is from ST plus 1 sample from this, where T is again going from 1 to infinity. So it's basically an expectation over several random variables right now. So what I'm doing here is uh, basically writing this expectation over several random variables going from T equal to 1 to infinity as firstly just the expectation over the first time step T equal to 0. So I'm asking what is S1, what is the expectation over S1? And then from then onwards, I'm writing the expectation from T equal to 2 onwards or T equal to 1 onwards. So this is basically expectation of S2 sampled from T. And this summation is over T equal to 1 to infinity now. So basically, I've just split the expectation into one time step here and whatever next time steps happen on the right hand side over here. So it was multiple expectations to begin with.
Yeah, and
Does that answer your question?
I suspect it gets to the heart of the question, and if there's a follow-up, please feel free to ask. But to like summarize that, it's basically saying if you have two variables x and y, and there's a function f of x and y, and you want the expected value of that function with respect to x and y, you can write that as first taking an expectation with respect to x, and you get something that is now just dependent on y, and then you take an expectation with respect to y. So just breaking down joint expectations into sequence of expectations. That's all that's happening here.
All right, so I can move on, but if there are any questions, I can go back to this and explain it again. All right, so now with that, let me get back to where we left off from last time. So we talked about the two settings of where learning-based methods come into play. First is for the RL setting, we don't have knowledge of the transition dynamics, so we don't know how the world works, how our actions affect the environment, and we don't know what the reward function is. So we don't know what are the good actions or what actions will lead to high reward or low reward. So this is going to be the setting of reinforcement learning. And the setting of deep reinforcement learning comes into play when we need function approximation, as is, for example, when there is a large or continuous state space. And the examples I gave last time were of chess, where the state space is just very large, or when you're processing images like games like Atari, when you need to have a convolutional neural network to understand the image in the first place and then take actions or predict Q values based on the understanding of the image. So in that case, we'll use deep neural networks to learn state representations, and I'll get to that today in some of the algorithms. Now let's take a look at what are the broad categories of RL algorithms. We saw that when we were doing just Markov decision processes, we looked at algorithms which do Q iteration and value iteration. And the first type of RL algorithm is going to be heavily inspired by Q and value iteration. So what it's going to do is it's going to learn the Q function by approximating the Q star with a deep neural network. And it's going to do so with finite data. So in value iteration, you were just iterating over every single state, action, next state in the state space, and you were updating your Q function. But over here, we're going to now try to approximately learn the Q function with what little data we have about states, action, next states, and rewards that we observe. The second category is policy-based RL, where we're going to try to directly optimize or find the best policy without worrying about predicting what the value function is. So in that case, we're going to parameterize our policy now with a neural network. So we're going to write pi theta star as where theta is the parameters of our neural network, which represents our policy. So I'm going to get to more details about that in the second half of this lecture, where I'm going to define what a parameterized policy is. And the third type of RL is model-based RL. This is not something we're going to look at in detail in this course, but basically what this tries to do is that we're going to have some approximation of the transition function as well as the reward function. So we're going to basically learn to approximate these quantities from the data we gather from the environment. So from S prime examples, we're going to try to fit a transition function, and we're going to try to fit a reward function. And with these approximate transition and reward functions, we can think of going back to the setting of MDPs where we knew the transition and reward functions, but now we know only approximate transition and reward functions. But even with that, what we can hope to do is try to plan by looking ahead, similar to what we did in value iteration or any dynamic programming algorithm. All right. So let's, without any further delay, let's dive into the first value-based RL algorithm, which we're going to look at, which is deep Q-learning. So before I start this, let me see if there are any questions.
Nirbhay, actually, would you mind going back a slide?
Mm-hmm.
I just want to make a couple of quick comments here. So this slide is a very nice outline of basically the three kinds of RL or three subfamilies of RL algorithms. You will often find in literature value-based RL algorithms, policy-based RL algorithms, model-based RL algorithms. And it's good to sort of have a roadmap in your mind. What sort of a paper am I reading, or what sort of technique am I using? That's number one. Number two comment I want to make is we are now getting into the part of the semester where we are beginning to treat neural networks and deep learnings as arbitrary function approximators. Throughout the course of the semester, we were sticking to supervised learning. And so the function we were approximating was the mapping from X to Y. That was the only function to be learned. And that's why we built MLPs, CNNs, RNNs, to learn that mapping from X to Y. Now we're heading to interesting applications of neural networks where that's not the only function. The X to Y mapping, it's not a supervised learning problem. But if you find any object, any mathematical object or any function where you can approximate it via data, then you can shove a neural network there, essentially. That's the crude way of saying it. But you head into reinforcement learning, you see, oh, I see an object called a Q function. I can fit a function. I can fit a neural network to approximate a Q function. I see a policy. I can fit a neural network to approximate the policy. I see an unknown transition function or a reward function. I can fit a neural network to do that. When we head to unsupervised learning, we will start looking at other sorts of functions. I see a conditional probability of z given x, where z is a latent variable, x is an observed variable. I can fit a neural network to predict that. And so it's this powerful tool now in your toolkit where we've just given you function approximators. You know how to construct them. You know the model classes. All that it will come down to is what is the objective function that you're optimizing to search in that model class, and where will you get the data. And a lot of what Nirbhay will tell you about today is where does the data come from and what is the objective function when we want to fit a neural network to a Q function, when we want to fit a neural network to a policy function, when we want to fit a neural network to a transition or reward function. Okay, back to you, Nirbhay.
Yeah, precisely. So as what Dhruv said, the basic formula for understanding any RL algorithm is just being able to understand two things. One is where is the data coming from, or how are you gathering the data? And the second is how are you using the data to optimize your neural networks. So those are the two things we should keep in mind when looking at any algorithm we're going to see today and in the future for RL. Okay, so with that, let me start with the first RL algorithm, which is deep Q-learning. So the intuition behind this is, given you have collected some data, you want to learn a parameterized Q function. So this parameterized Q function is going to be our neural network, which outputs our Q values. So let's say in the simplest case, we have just one linear layer as our Q function. This has been studied extensively in the RL theory literature, and people have shown that this is quite an important tool to understand some theoretical benefits of Q learning. And people have shown that there are some, you can actually prove the convergence of some algorithms with just linear function approximators, where you have just one weight vector W multiplied by your state vector, and you have some scalar bias added to it. But however, in recent years, RL has become popular because people have been using very deep Q networks, which have been shown to work well in practice very recently. So the first paper which came out, which introduced deep Q networks, was, I guess, the 2013 DeepMind paper, where they showed how to play Atari games with deep Q networks for the first time. So an example of such a Q network is shown on the right. We have a state space, which is the image pixels you see here of this Atari game, which is called breakout. So you have to control this paddle over here to make a ball hit these bricks. And every time you hit a brick, your score increases. And that is your reward. So your reward is visible on the screen. And what the agent sees are these RGB image pixels. And in this specific architecture, they use the last 4 frames of the images as a state representation. They feed it into a convolutional neural network, which is in this case 2 CNN layers, one fully connected layer, and one output layer, which gives the Q values as output for all possible actions starting at this state. So if this is the state S, and these are the previous states ST-1, ST-2, and ST-3, this Q value will basically be giving as output the Q function of ST and AT, and it's going to do it for all possible actions. So let's say in this case, there are 2 actions. We can either move the paddle right or left. Then it will give 2 Q values, the Q value for taking the right action and the Q value for taking the left action. So this is an example of how people have used a CNN to understand images and use their understanding of images to predict Q values of a given state. Now let's look at some demo of some Atari games. So if you recall this slide from the first lecture, the setup for Atari games is as follows. The important thing to note here was that the state space is going to be the state of the game right now as you see it. So it's going to be the RGB image pixels you see on the screen right now. And just from that, the agent is supposed to have to learn a CNN or a deep neural network to understand the image and use that to predict Q values in the game. So let's see the demo. So this is again for the game called Breakout. And this is the video for the DeepMind's Deep Q Learning paper from 2013. So is this visible, Dhruv? Okay. So as you can see in this video, there is all right. So this is what it starts with. What is happening is that you are seeing the agent in the algorithm play the game right now, and you can see it starting randomly. So it currently doesn't know how to play the game, so it's failing at it, but it is somehow learning and managing to get better at the game. So you can see that after some more minutes of training, it's starting to play even better. Now what it has learned to do is that it has learned to control the paddle such that it keeps the ball in play, and the ball keeps hitting the bricks to break them and increase the score of the game. So now it has learned to that when the ball does not hit the paddle, it's a bad thing. You get lower reward, and if you keep the ball in play, you get higher reward. So these are the things it has learned so far. Okay, so as you read there, it has now learned to a very particular strategy to get extremely high rewards. What it has learned is to carve out one specific vertical column of bricks and then let the ball just stay up and rack up points. And this happened after a long amount of training. So now getting back to what, after looking at how this DQN model is training, we're going to ask again the same 2 questions. What we just saw was an agent interacting with the environment to play the game. Initially, it was doing bad, but eventually, as it kept playing, it got better. So it's trying to do 2 things at the same time. It's trying to first propose a policy to play the game. That's what you're seeing right now. You're seeing the policy in play. And as it keeps playing the game, it's gathering experience or data, and it's using that data to get better. So the 2 things that are happening is that it's gathering data, and it's using that data to improve its model. So for this algorithm, we're going to keep in mind these 2 questions. How is it going to gather data, and how is it going to use that data to improve its model? For the first part, we're going to now assume that, yeah.
There is a question about, so there's a compound question.
Yeah, I was there. So now again, what I was talking about was that we need to focus on 2 questions to ask whenever we see a new RL algorithm. We want to ask the question, how do we gather data? And we want to also ask the question, given that data, how are you going to optimize your model? So let's focus on the second question first. Let's assume for now that someone has provided a data set for us of state, action, next state, and reward tuples. And we have a data set of, let's say, n such tuples. And we don't know how this was collected. It may have been some good policy. It may have been a random policy, but that doesn't matter for now. Let's just assume we have this data, and what can we do with it? So what we're going to do is define an optimization objective given this data. So if you recall the Bellman optimality equation I presented at the start of this slide, we had written the Q star of SA recursively in terms of itself and the reward at the first state and action. And from the last lecture, we saw value and Q iteration, where we had basically written the Q iteration update as Q of I plus 1 equal to this thing plus where we wrote Q star, the old Q star is Q of I here. So for every one iteration of Q iteration, I'm updating my Q I plus 1 with the old estimate of Q, which is Qi. So I've put the old estimate of Q in blue color and the new Q, which I want to update in red color. And if I were to translate this loss and this the objective, which was similar to Q iteration, into a loss which I can optimize for my data set of n example points, what I would write it as is follows. So what I want is basically my predicted Q values from Q new. I want them to match my reward plus gamma times max of old Q values. So let's say this is the target which someone provides me. I want to basically have a neural network which predicts this target. But now the problem is that the thing that I want to predict and learn, that neural network is also producing partially the target which I want to optimize. So you can ask the question, should I learn or back propagate gradients through just Q new or Q old as well? And the answer to that is that I only want to back propagate gradients to Q new. And the reason for that is as follows. Sorry. Actually, let me get to that a bit later. But basically the thing I wanted to say here is that similar to Q iteration, you want to iteratively update your Q function or Q network to match this target, which will be similar to the fixed point algorithm, which is Q iteration. So as in Q iteration, I showed you that what a fixed point algorithm just does is that if you have a y equal to x line here, and you have some function here, f of x, this algorithm will basically converge to the fixed point of that algorithm. So it will try to find a Q new to update such that it satisfies this Bellman optimality equation. And it's going to do that over the SA S prime R data set, which we have here. So this SA, let's say, is some one member of the data point here. And my S prime is the ground truth next state, which I observed in this data point. And my R is the ground truth reward I obtained from taking action A at state S. So I'm going to try to estimate my Q values from this data set. And before I go into why or which network to update, let me first talk about how the forward and backward pass would work out. So let's now assume that. Yeah.
Nirbhay, would you mind going back to the previous slide? Yeah. So I just want to quickly add, this is a common. So this is the second time we're seeing a trick like this, where so the center expression that says Q star as expected value of R plus gamma times max over A prime of Q star, it's a recursive definition of Q star in terms of itself. And last time in value iteration, we saw that we can convert recursive definitions into iterative algorithms by just making iterative updates, treating the right-hand side as a operator that fly over and over again. This time on this slide, what we're presenting is an alternative way of doing this, that if your Q is a parameterized function in terms of some parameters, then you can just say that, look, what I want at optimality is for the right-hand side to be equal to the left-hand side. And so I'm just going to penalize the squared difference between the right-hand side and the left-hand side. And that's what the MSC loss is doing, right? It's taking we don't have access to Q star, but we have access to Q currently with our current setting of parameters. And we have access to the right-hand side, which is one sample estimate of the expectation. So instead of actually computing the expectation, I'm just going to take my data set and feed in the SA S prime R, and I get the right hand side expression. And I'm just going to say, look, the left hand side has to be equal to the right hand side. Therefore, the difference of squares of that's my objective function that I'm minimizing. The less deviation there is, the better I'm doing, because I know at optimality this objective has to be 0.
Exactly.
Okay.
Yeah. Thank you.
Back to you.
Yeah. So let's talk about how I'm going to predict these Q values in a forward pass and how I'm going to take the gradients of this Q value in the backward pass. So let's say now I have a batch of B data points. So I have B tuples of state, action, next state, and rewards. What I'm going to do is, as is in batch training, I'm going to have a batch of states which I'm going to give as input. So this S here of this tuple, I'm going to give as input to my Q network. And what it's going to give me is it's going to pass through this state and predict B outputs. So every single output in the batch is going to be a vector of n actions, of size n actions, and what it's going to give me is basically the Q value, Q SA value for for that particular action given that particular state in the batch. So again, if this is my Q network, I'm going to take as input my state representation, and the last FC layer of my neural network is going to produce, let's say in this case, if I have two actions, it's going to produce two values per item in the batch. And now what you have produced as output of this network is the predicted Q values S, A for every single S, A in this data set of in this batch of B items, right? And now in this batch, you also have the true reward, which was here for every single SA, and you have the true S prime in the batch, which was the true next state you got from that S and A. Now with this, I'm going to compute the L2 loss as Dhruv pointed out. We want to just minimize this quantity, and at optimality, these two quantities should match. And now I'm going to treat my Q network here as Q new. So let me call the parameters of this Q network as theta new. And I'm going to also assume that my Q old is also a parameterized Q network. And let's say the parameters of this Q network are called theta old. What the gradient I'm going to backpropagate is only for Q new. I want to make sure that my Q new matches the target. I don't want to make my target match my prediction. That's important. So in my backward pass, what will happen is that I'm only going to update the theta new parameters of my Q new prediction. And I'm going to freeze or keep fixed my theta old parameters. And why is that the case? So what happens in practice is that when we optimize this loss, whenever you update Q new, if you had the same network here, you will update that network here as well. And that will lead to your prediction update leading to change in your targets very rapidly. And that turns out to be quite problematic. So what people have proposed is that they've proposed to fix or freeze the Q old network for some time. They want to just update the Q new parameters for a few iterations and after some few data points. And at every few regular intervals, what's going to happen is that you're going to set Q old back to Q new. So let's say you do 10 iterations of updates where you want to update Q new and keep Q old fixed. After 10 iterations, you will again set Q old with the parameters of Q new. And why is that the case? Because this is a fixed point algorithm. You want these two quantities to match, but you cannot keep Q old fixed all the time because it will be inaccurate. It will learn sequentially. So the more times you do this process of learning Q new and then setting Q old to Q new, you'll eventually get to a point where this loss is minimized and the left-hand side matches the right-hand side. So there's a question. Yeah. Sorry, Dhruv, go on.
Actually, yeah, if I can just add to this, we are using intuitions from linear regression and regression with neural networks. So here, the Q new is playing the role of y hat, the prediction from our neural network, and the R plus max over a Q old is playing the role of y GT, right? So that's the target, and Q new is our y hat, the prediction, and we have squared loss. Now, the weird thing here is that our targets contain as sub-functions our own parameters. They depend on our own parameters, and that does not happen in regular regression. The pathological case here is that if you did not do this Q old, Q new trick that Nirbhay is showing, if you did not do that, if you optimize both over theta new and theta old simultaneously, if you said they're the same parameter, let's assume R was 0 in this case. At this time step, let's say you did not get any reward. Now, if that was the case, what this loss would be encouraging is for Q new and Q old max for the max action to essentially be the same, for their difference to be penalized. And so one way of minimizing that difference is to set both the Q function values to 0. And then you are getting these pathological cases because your targets are also a function of your parameter. And so that's what this trick is trying to overcome. Okay. There are a few different questions in the Q&A panel, but you should probably look at them.
On now. Yeah, given that this is the forward and backward pass, now one thing we can do is that if someone has actually given me a data set of these experiences, let's say some fixed robot has already interacted with the environment and produced this data set, we can still learn something meaningful. There's an algorithm which is called fitted queue iteration, which the whole assumption of this algorithm is that someone is giving you this data set, and if you repeatedly apply or try to minimize the mean square error loss, you will converge to a Q value, which is the best you could do with that data set. And that is the output of the fitted queue iteration algorithm. But now let's get to the second question we want to ask when we look at any RL algorithm. We want to ask the question, the second question is that how do we get the data in the first place? So let me see if there's any question first. How do positive and negative rewards values affect the loss function differently? Let me actually get to that question a bit later. Let me first finish this part and then get to that question again. Okay, so now to answer we have to ask the question, how do we gather the experience in the first place, or who provides us this data of SA, S prime, R prime? So if you saw the video from last time, the agent was actually providing some policy with which it was interacting with the environment. So you could see initially that in the first part of the video, it was doing pretty bad. It was taking random actions. It was failing to do its job. And eventually it got better. So one thing we're going to look, one thing which is going to be important to answer this question is that, and I feel this is personally coming from my experience with RL, is that this answering this question is the reason that RL is going to be quite hard. And I'm going to get to why that is the case in the next slide. So now let's have a thought experiment. Let's say that you provide some policy PyGather. And let's say for the sake of the same example, you have the environment, which is the Breakouts Atari game. You have this environment, you start with a policy. Let's say you have a pretty bad guess to start off with. You have a random policy. So you have this random policy, it interacts with the environment, and it produces some data set of n examples. Now, what will happen is that you want to use this data to train a policy. Let's call it PyTrained. What will happen is that if your policy is random, it'll try to move the paddle in random directions, and only some of these data points will be such that the ball hits the paddle and actually hits another brick and gets positive reward. So out of this data, there'll be a few SA, S prime, R examples which actually have positive reward. So what will happen is that with those data points will actually push our training to tell that the Q value for hitting the ball or keeping the ball in play is actually high. And with that, we can, let's say, have a policy which says just follow the maximum Q values. So with this data of random examples, I can train a policy to try to keep the ball in play by making the paddle hit the ball. And now what I can do is that with this trained policy, I can now overwrite my PyGather and say that I'm going to replace it with PyTrained. So with the data I just gathered, I have improved my policy by doing a greedy estimation of the Q function which I just learned. And I'm going to put this new policy back into the environment and tell it to gather more data with this improved policy. And as this loop goes on, you saw in the video that the policy got better. So eventually what happened was that as it learned to keep the ball in play, through random chance, it also discovered that in one particular case, if the ball actually went through a vertical column of bricks, it reached the top part of the screen and it kept bouncing here and it got really high reward. And that really high reward was a very good behavior. So since the reward was high, the Q value for that doing those actions was very high. So it wanted to do it, keep doing it. So it wanted to change its strategy from just surviving and keeping the ball in play to actually trying to make the ball reach this area here. But now the problem was that we saw in the video that happened after quite a long time. It kept training, it kept getting this experience, learning that the ball has to be in play. And only by random chance did it actually discover that doing the strategy of going up is a good thing. So now the problem is that if there are some strategies which just don't happen by random chance, it's very hard for your policy to discover them. So one key problem will be in any RL algorithm is the problem of exploration versus exploitation. So given, let's say that a decent policy it has learned is that keeping the ball in play is a good strategy. If it can keep doing that and it can exploit that, given that it can exploit its current knowledge of how to play the game. But if by doing so it is not exploring the game further, it may never uncover strategies to do better than it's currently doing. So one thing we'll always have to define in our algorithms is a way to explore or try out actions which the agent does not know the outcome of, or in which case the agent doesn't know that it will get the same reward it's getting currently if it tries those actions out. Because what will happen is that exploration is going to be essential to discover any new strategy. The other problem that happens because of this loop is that if you notice, your pie gather is producing some data, and your data is again being used to produce a new policy pie gather. So what's happening is that you are producing the data you want to train on. So if you see that why that is a problem, the problem is going to be that your data is not going to be ID anymore. These data points are not going to be independent samples from your entire state and action space. That's not going to happen. You're going to get only the state and actions which your policy currently thinks is a good strategy. And because of that, your data is going to be highly correlated, and there can be some problems like feedback loops. So your policy can only be happy with what it's currently doing. It will never try to improve beyond that. It can get stuck in local minimas, and we're going to see further explanations of that soon. But let me see if there are any questions.
While you look at those questions, I just want to make a couple of comments here. So the answer to the question that people have asked a couple of times, where does data come from? Well, you go out and gather data yourself. The agent or the policy goes out and gathers data. So that's number one, the answer to that. And I think this slide right here that Nirbhay has on the screen, it really illustrates both the fascinating generality of RL, but also its difficulty and ultimately bleakness, if you will. In my mind, I view RL as like the harshest possible learning scenario, where you wake up in an environment, you know nothing about it, you don't know how the world works, you have no knowledge of what to do, you take an action and you get feedback. Either things work out well, in which case you maybe get food, or things don't work out well and you get hit on the head. And you don't know whether it was the last action you took that caused that, or it was the last 20 actions, or there was a sequence of very intricate last 200 actions that you took, and exactly that sequence of actions causes positive reward to emerge or negative reward to emerge. But you have to figure all of this out. And by the way, you never get to go back in time. You are always acting, and so you can only learn with the data you gather, as opposed to any other learning scenarios or any other data sets given to you. And so, there are, of course, analogies or takeaways for life. Like, this is why, for example, at least the advice that I give to my students is do not self-select, because you are choosing the data that will come towards you. If you do that, you should go out and try various things and apply for opportunities that may seem a bit out of the reach. But this is going to be also a problem if we are going to seriously consider reinforcement learning as an approach towards developing intelligent machines. In that, if you look around you, that is not how, for example, human populations develop, right? There is no notion of a population in RL. There is a single agent. That single agent learns from scratch everything about the world and the task. And we know that is not how human or other species functions. We know that we sort of get taught by other generations that came before us. There's a sort of cumulative knowledge that accumulates, and none of that is present in this learning paradigm. That's fine. I think it's a perfectly valid mathematical abstraction, and it's a learning paradigm worth studying to get started, but it's important to keep these things in mind. The generality comes at a cost. That because you can frame your problem as an RL problem, often doesn't mean that you have a solution. It just means that you now have two problems. The original one that you started with, and the RL problem that you now have to solve. Okay, back to you, Nirbhay, and I think there are a couple of more questions that have come in.
Yeah. So one unanswered question I want to answer right now is someone, again, I said that if we answer the question, what is the policy we use to gather data? One thing we could do is just be greedy and say that what is the current queue function I've learned? Whatever that is, I'm going to pick the argmax action of that at every step. that is one thing I could do. But as we saw earlier, what could happen as a result of this greedy procedure is that I could get stuck in local minimas because I will never explore actions which I think are not meaningful right now. But exploring those actions will actually possibly lead to better strategies to solve the current task. And this will just not happen if I just follow this greedy strategy. So what people have been using, and a thing which is a very popular approach right now, is what is called as Epsilon greedy exploration. What it means is that given a Q function which you're currently learning in your algorithm, with some epsilon probability, you're not going to follow that argmax. You're going to choose a random action with some epsilon probability, and otherwise you're just going to stick to your best guess or best argmax action with the Q function you have learned. And with this small probability, let's say epsilon is like what people usually have is like epsilon. They start with a high epsilon of 0.5 and they eventually decay to, let's say, 0.1. What this will ensure is that you always try out novel actions at states you've already visited. So this is one way of ensuring that you always explore in every possible state. And we'll see in the algorithm that this was actually quite helpful for learning the DQN algorithm. So there's a question: is S prime the expected or actual state after taking A from state S? Yes. So the answer to that it is the actual state. It is not a distribution over states. It is as if you sampled from the distribution of possible next states given that S and A. So it's one sample from that distribution. It is the actual next state which the agent encountered while taking that trajectory. Okay. And now that we have answered the question of, let's say we fix the exploration problem by having an epsilon greedy policy. Now, what can still happen is that the data you gather is with the policy you used, and that's the policy you're going to train. So what can happen is that your samples are highly correlated. You're not going to get independent samples of all possible state and actions in the state and action space. And as a result of that, you're going to get very high variance gradients, and that's going to lead to very slow or inefficient learning. And an example of that from an environment we saw earlier is that, let's say we are again in this linear world, and somehow the random policy chose to go right and find that this reward of +1 is received from going right. Now what will happen is that since this is what the agent discovered first, it will collect data from going to the right more and more. So more of these state and actions will be on the right hand side of this state space, and it may never actually explore the left hand side. It may never know that if it actually takes different actions from what it's currently taking, it may lead to a reward which is higher than the reward it's currently getting, because this is the truly optimal thing to do. The best thing to do in this environment is actually go left. So with epsilon greedy exploration and another fix to this problem, in order to fix this highly correlated dataset problem, people have proposed the following strategy. What we can do is that in addition to epsilon greedy, what we can do is have what is called as an experience replay buffer. So what it means is that it's going to just have a data set of experiences SA, S prime, R prime, and it's going to store experiences even from an older policy. So during training, you're continuously updating your policy, but you're not discarding the experiences gathered from your old policies. You're keeping all of them in a finite sized buffer. And the key is that we're going to now train your Q network, not from the latest data you got, but you're going to randomly sample mini batches from this entire data set. So there's some probability that you're going to sample your SA, S prime, R tuples from older experiences, or it could be from your newer experiences. You're going to weigh them equally. And this is just a heuristic which people have adopted, which turns out is quite useful and quite helpful in learning. And what people have observed is that the larger is the buffer, the lower is the correlation between your data points which are in the buffer. And if you do this random sampling strategy, you more or less mitigate the problem of correlated data points or high variance gradients. Now I've introduced two strategies. One is epsilon greedy and one is experience replay. Now I wanted to look at the algorithm from the 2013 DeepMind paper, which I've shown in this slide, but I wanted to look at it offline. I don't look at what all the procedures are written here right now, but I wanted to look at three key components of this algorithm. One is that the fact that there's an experience replay buffer being used. The second is that the policy used to gather data is epsilon greedy. And the third thing I wanted to look at is the update rule, which is used to update the Q function. you'll know that if you understand these three components, this is basically everything that is there to understand in the deep Q learning algorithm. So take a look at this offline and see if you can understand what exactly is going on now that you know every single component that's going into place in this algorithm. All right. So now with that concludes the discussion on deep Q learning. And let's see, I have 15 more minutes. Let me try to get into the second half, which is policy gradient. So let's see if there are any more questions before I move on.
No, I've answered all the questions that came.
All right. All right. So I think I should go slightly faster if I want to cover everything I want to cover in policy gradients. All right. So we've looked at, in the start of the three lectures, some methods for solving MDPs, which is going to be saying, if you know your transition and reward functions, which is the case of MDPs, what you can do is you can use policy, Q, or value iteration to get the best possible strategy. And this is going to be a dynamic programming approach. We also looked at the case of RL, where we don't know the transition and reward functions. So we saw that if we estimate the Q values, that's going to be value-based RL. If we estimate the transition and reward functions, that's model-based RL. But now what we're going to look at is a method which does not use any of these things. It's going to directly try to update the policy without worrying about predicting Q values, predicting rewards or next states. It's just going to see what is the best way I can improve my current policy. Now, as it was with deep Q learning, I'm going to now try to answer the same two questions. The first question is, for this algorithm, how am I going to collect data? And the second question is that given that I've collected data, how am I going to update my models? So in this case, what is my model? My model is going to be a parameterized policy pi theta, which is just a mapping from states to actions. So this may be a neural network, which takes as inputs a representation of a state, and it produces probabilities over every single action. So I'm going to assume discrete actions for now. And I'm going to write my objective as this J function. So J of pi is going to be defined as the performance of this policy pi in terms of how much reward it's going to get. So for the sake of simplicity, I have assumed that gamma is equal to 1 for now. So there's no discount factor here. And my trajectories are finite. So they're only going from 1 to capital T. So I'm going to just say that the performance of my policies is the expected reward it's going to get over the entire trajectory and summed over 1 to T. And now this policy is quite an abstract notion. Since I've introduced parameters of a policy theta, my theta completely describes my policy. So whenever I write pi, I can actually substitute in my optimization problem theta. So instead of writing pi star as argmax over all possible policies in the policy space, I can just say I want to find the best set of weights theta among the set of weights which, let's say, are in R power D, some d-dimensional space. And you're going to try to maximize the same objective, which is the sum of rewards in a trajectory. All right. So now let's take a look at the Pong example we saw again. What would a policy look like? In this case, the state space are the pixels which are being observed right now. So if this is the image which is given as input, your policy will probably be some neural network which can have some layers. And at the end, it will output the probability of each action. So let's say there are two actions right now. Action can either be going up or going down. So what it needs to output is just the probability of going up, because if it's not going up, then it has to go down. So in this case, it has to only output one single log prob. And now with this neural network definition, let's take a step back and get some intuition as to what do we want to happen? Like, what is a good thing to do in this case? In supervised learning, you know that if you do a task of, let's say, image classification, we have images given as input. We have some neural network which you can forward pass the image, compute the log probability of every class, and I'm now going to call my classes as actually actions. And you have supervision for what the correct action or label is. So you know that if you predicted a higher probability for the wrong label, you will get supervision saying that this is the actual correct label, and you should increase the probability of selecting this label. That's the signal you get from supervised learning. Now, let's say what I want to do is that in reinforcement learning, I have the same image as input. I have predicted log probabilities of two actions, and I took an action now. I don't just predict both actions. Let's say I sample an action given these log probabilities. Let's say my sampled action was 1. With this action, what signal do I get? The only signal I get is the reward for taking that action A. So let's say I got a reward of -1 for taking that action. Intuitively, what I could do is that I look at the reward and see that it's bad. It's quite bad. It's negative. I don't want this to happen. One intuitive thing I could do is, let's say I reduce the probability of that action and scale it with the magnitude of the reward. So given that the reward is -1, I reduce the log probability of that action and then I backpropagate it through my neural network, same as before. And this intuition is basically what is going to lead us to the algorithm of policy gradients. I'm going to formally explain how this procedure is going to happen, how we're going to use a reward to scale our gradients for the actions that we did choose. But for now, this is the intuition that you should keep in mind when you think of how to update a policy with policy gradients. Now, before I move on to the formal definition of the gradient, let me first talk about the second half of the RL algorithm, which is how do we gather data. So this is going to be quite simple for policy gradients because you already have defined a policy. So, sorry, let me get to this first. Yeah. So I'll get to that slide again. So given that you've already defined a policy, pi theta, what we're going to do is that we're going to sample trajectories given the policy pi theta by acting according to pi theta. So this is, let's say we've sampled n possible trajectories, and for every single trajectory, you have the reward that you got at every single time step. So this first summation is going to add up all the reward for a trajectory, and the second summation is going to add up all my trajectories. So now you can think of this as a mini batch of data, where given I've sampled some n trajectories, I can estimate the reward I got following the current policy pi theta. And the previous slide was basically to introduce some different notation. So I'm going to now write, since I'm not considering discounting at all, the gamma factor is not there. I'm going to slightly change my notation. I'm going to write my tau as depicting an entire trajectory of going from t equal to 0 to capital T. So I'm going to write pi theta of tau, which is going to be equivalent to p theta of tau, which is just the probability of a sequence tau under my policy. So as you've seen in sequence models, the probability of a sequence is basically the individual probabilities of the sequence elements given the previous elements in the sequence. So I can write it just as the probability of the first state times the probability of the next action and the next states given the previous action and previous states. And since it's a Markov decision, we assume the Markov property, next states only depend on the immediate previous states and the immediate previous actions. So now I'm just change my notation slightly to rewrite my maximization problem as maximizing over an expectation over trajectories sampled from my policy itself. All right. So with this change in notation, I'm going back to, we know already how to gather data. So now that we have, what all do we know about policy gradients? We know that given we have defined a policy, it's very easy to define how to gather data. We just use the same policy we have to gather some experiences. So with that, we can gather some data set of n trajectories. And now we want to update our policy using the intuition we just saw earlier. So intuitively, what I want to do is that if I have high reward, I want to promote my policy to take those actions more. If I get low reward, I want to tell my policy to stop taking those actions. So like reduce the probability of predicting that action at that particular state. So how is that intuition actually coming about? I'm going to now give you a formal derivation of why that intuition is coming about. But before that, let's first look at, let's assume for now that the policy gradient is some expression here. So don't look at this for now. I'm going to derive this. But given that you have some policy gradient right now, the algorithm has all the parts filled in. You already know how to gather the data of trajectories. You can update it with the policy gradient. And you can now update your theta parameters as if you're doing gradient descent. So with the gradient, you just have some learning rate alpha and you update your policy parameters theta like this. So this is going to be a simple gradient update step. And all we need to focus on right now is our understanding of how is the gradient derived. So this is what I'm going to tell you now. How do you exactly get the gradient of a policy, the reward of a policy? So let's see, you have 3 more minutes. Let's see if I can cover that, the gradient. Okay.
Nirbhay, one thing we can do is we can carve out maybe like 10 minutes for you in the next lecture, in Johan's lecture. So I think you can proceed at a normal pace and cover this derivation, but don't feel free to cram the rest of the things. We can.
Yeah. So I have a few lecture slides after this. I'm just going to explain actor critic in one slide. So let me just conclude by this derivation then. That's
Yeah.
all I'll do for this lecture.
Yeah. Sounds good.
Okay, sounds good. Okay, all right. So what is our objective? Our objective is j theta, and recall that I have replaced my policy with theta because theta is basically the entire policy. It represents all the parameters that are used in my policy, and I want to now compute the gradient of this objective. So I want to maximize the performance of my policy. So what I'm writing down here is in what direction should I change my parameters such that the performance of my policy improves. So by definition of this performance, I have on the right hand side the rewards I get from that trajectory, and the expectation is the trajectory is sampled from my policy p theta or pi theta, and I'm going to try to take the gradient of this expectation. And the derivation is going to go as follows. I'm going to first write my expectation as an integration with the probability distribution p theta, which I'm also written as pi theta equivalently. So now I have the probability of the trajectory tau, the reward for the trajectory tau, this integration and this gradient here. So I'm going to first switch the integral and gradient, which I can do due to continuity of these two functions. So I'm going to first exchange the integral and the gradient, and now in my inside of my integral, I have only my pi, which depends on the parameters theta. The reward does not depend on theta. What I'm going to do now is try to multiply and divide pi theta in this expression. Why am I going to do that? So when you have pi theta in the numerator, you can replace an integration of pi theta times something with an expectation over pi theta. And that's the reason I'm going to multiply and divide pi theta. And there's another trick which is going to be used. We know that the gradient of the log of a function is 1 over that function times the gradient of that function. And now given these two quantities, my denominator and my grad of pi theta are basically these two quantities here. I can replace this ratio with the gradient of log of my policy. So that is basically what I do. What I do is that this term is replaced by grad of log pi theta, and the numerator is what I want now. I have a pi theta in the numerator. And why is this useful? If you see here, this is an integration of some probability and some function over here times d tau. This now can be written as an expectation. So I can write it as expectation over tau sampled from pi theta, which is the distribution here. And the remaining thing inside this bracket is basically the function I have on the right hand side. What I have done is now converted what initially was a gradient of an expectation into an expectation of a gradient. Why have I done that? If you note that you can easily compute the expectation of a gradient. You just have to have multiple values of this gradient and then take the mean. That is how you approximate an expectation. But computing the gradient of an expectation is something difficult. It's not possible. Like you need infinite samples to actually compute that accurately. But with this simple derivation, what I've been able to reach is a form of the gradient which is easy to compute from some finite samples. So all I need to do is compute some trajectories, compute the log probability of these trajectories, and I can easily compute the gradient of that because that's what I've been doing in supervised learning. And I have now multiplying the gradient with the reward here. So this is the key intuition right now. If the reward is positive, this will make sure that the policy promotes the log probability of those actions to increase. And if the reward is negative, it will tell the policy to decrease the probability of those actions being chosen. So that's the intuitive explanation for this. And I'll get to using this in the algorithm again in the next class, I guess.
Okay, excellent. Thank you, Nirbhay. So we are at time.